We spent a whole unit last term talking about gases, and you know that gases can cause pressure by running into the walls of the container that they're in. Every single liquid that you can think of is going to have some molecules, some number of molecules sitting above the liquid itself in the vapor phase. When I say vapor, I throw that term around and have before, but I don't know that I've really defined it. Vapor is just a gas that is in contact with its own liquid. So if I look at these water molecules right here and here and here and here, they are all water vapor molecules. They are molecules in the gas phase sitting above their liquid. And you know that each one of those molecules is going to run into the sides of the container that it is in, and they cause pressure. That's called vapor pressure. The more molecules that you have in the gas phase, the higher the vapor pressure is. It might not surprise you that for a molecule to get to the gas phase, it's got to break free from the other liquid molecules it's surrounded by. So if I look at some of these water molecules in the liquid phase, if they want to get up into the vapor phase, they want to be gas molecules, they've got to break a couple of hydrogen bonds to get there. And that's hard to do. So this is the first time we've had a property where there's really an inverse relationship between the strength of intermolecular forces and the property itself. In other words, what I'm saying is molecules that have really weak intermolecular forces tend to have very high vapor pressures, and molecules that are really strong in terms of their intermolecular forces tend to have low vapor pressures. Why? It's hard for molecules with strong intermolecular forces to break free of the liquid and to get into the gas phase. Let's look at 4 different molecules. This is actually a pretty complicated graph. And the first thing I want to do with this graph is just look at one point on the graph where 3 or 4 molecules might exist. So if I look at like 20 degrees Celsius, I'm just going to mark 3 points. One for a molecule called diethyl ether, which is right here. One for a molecule called ethanol. Go back. One for a molecule called ethanol, which is right here. And one for a very famous molecule called water, which is right there. And at 20 degrees Celsius, which is about room temperature, here's the take-home message. The water molecule has the lowest vapor pressure. You can see that on the y-axis. The ethanol has a somewhat higher vapor pressure, but it's still pretty low. And the diethyl ether, it has a very high vapor pressure. So the question becomes, why is that? Well, when I look at the water Lewis structure, first thing I would note about water is that it's capable of making hydrogen bonds. We know that because we have 2 H's that are attached to an O. They're ready to make hydrogen bonds, and we know that hydrogen bonds are strong. If you also look at ethanol, it can also make a hydrogen bond with this H right out here. We've talked about that before. So the question is, why do you think ethanol has a somewhat higher vapor pressure than water? To me, it's in the number of hydrogen bonds a molecule is capable of making. Water can make a hydrogen bond with this H and with this H. 2 hydrogen bonds, that's better than 1. And that's all that ethanol can make is 1 hydrogen bond. Compare that, though, to diethyl ether. Diethyl ether is not a nonpolar molecule. It's actually polar. I can tell that even though it looks symmetrical here, it's got those lone pairs on the oxygen atom in the central position. That makes it polar, but it only displays dipole-dipole interactions with other molecules. Again, why is that? Well, none of the H's in diethyl ether are capable of making a hydrogen bond. They are not directly connected to O, N, or F. And so we don't expect diethyl ether to make hydrogen bonds. Therefore, it's got weaker dipole-dipole interactions and a higher vapor pressure. It's easier for diethyl ether molecules to get to the gas phase. Let's do one last comparison. Look over here in green, kind of the lowest of all of them. The one that has the lowest vapor pressure is a molecule called ethylene glycol. If I look at it, it doesn't look too much different than ethyl alcohol, ethanol. But unlike ethanol, it has the ability to make two hydrogen bonds, just like water can make two hydrogen bonds. But it's also heavier than water, and so its London dispersion forces are stronger than water. Okay, well, that makes sense that it would then have a lower vapor pressure than water because it has stronger intermolecular forces. One last thing on this before we call it good. Let's talk about why there is a temperature dependence when it comes to vapor pressure. If you look at just the ethanol curve, which is the second from the left, we see that the vapor pressure goes up as temperature goes up. That's true for all substances. Think about why that might be. When you increase the temperature, you're making molecules move faster. They have more energy. They have more energy to break their intermolecular forces and to escape the liquid phase and to become gas particles. When they become gas particles, they cause pressure. That's why the vapor pressure is higher. Okay, we're going to watch one last video and then we'll meet back again. Take care.